We are the compromisers, and my name is Isabelle, this is Lindsay, Lucas, Danilo, and Ricardo. And our project is about the recovery tank effectiveness. So first of all, a little bit of just background information. The WC Creamery uses a clean in place system, CIP, to clean large equipment, including pipes and tanks. Equipment is washed with fresh water, basic soap water, and acid water in order to sanitize. And they have a recovery tank that collects the wash water and neutralizes by combining the basic water and with the ice water, and before discharging it to the seaway system. So our problem statement is this is our recovery tank, and as we can see, there is some of overflow on the floor, and the recovery tank is not large enough to hold all of the water, wash water for the pipe CAP system. So because of this, water overflows for the recovery tank, and it's sent to the sewer without being neutralized. And if the water is not correctly neutralized, the creamery could be shut down by the environment agencies. So our original goals was perform a cost analysis study that focused on buying a new tank, or analyze the amount of water generated in the CIP system, and possibly change the current cleaning program. It includes valves or change pipes, or not pipes, but change the system and increase the pump or power to create a turbulent flow with less water, or change in the cleaning steps. However, we just figured out that we wouldn't be able to do the second option because we don't have enough time, and we determined that changing the CIP system to use less water was out of scope, and it's because of the limited time. So instead of this, we just focus on deciding whether or not buying a new tank would be effective, and this analysis would include which kind of tank would be better, or which size. If a small tank just for the overflow would be better than a larger tank for the entire recovery water. So.
All right, so these are some numbers that were sent to us by the folks at the creamery. The current recovery tank holds about 100 to 120 gallons. And these are some of the estimates of the water used in their CIP lines. And as you can see, some of them are 3 times as large, or 3 times as much water as the recovery tank can hold. So obviously there's a problem. And when the water overflows, it overflows from the top of the tank. So in order to measure, we decided to measure the pH of the water that's overflowing to make sure that it actually is a problem and that it's not neutralized. So we were told that the target is a pH from 5 to 9. So when we waited for the tank to overflow, and we recorded the time that it did overflow, and so we took cups and put it up against the tank when it was overflowing, and we did that 3 times, once at the beginning, somewhere in the middle, and once at the end. And we repeated this 15 times. We had 15 different data sets. And then we tested the pH of the samples. Like I said before, the creamery wasn't really sure if the pH of the water was within spec. So we decided to take the pH. We collected 3 different samples to check to see if the pH really changed as time went on. And we also took them on different days to see if different operators made a difference, or if they were making something different. We wanted to see if that affected the pH at all. So this is our raw data, and as you can see, none of our numbers are outside of the specification limits that we were given. So that was a good thing. But they are a little high. Most of them are above 8, but below 9, so we're still okay.
Okay, so after we collect all this data in the measurement part of our process, we decide to perform some statistical analysis to see how good or how bad our process was doing. And here we have the first results for our data, the pair XMR and the MRR chart. But just a parenthesis now to explain a little more about these charts for those who are not as familiarized with this as us. When we are collecting data, we can we can have 2 different groups of charts. The ones that are related to the variables, for example, time, pH, temperature, as ours here. Or we can have charts that are going to group data from attributes, for example, conformity or non-conformity about color of, I don't know, an apple lodge, a color of this. As I said, we have pH, so we need to use a chart that is going to deal with this variable data. And within this category, we have kind of few graphs that we can use. We decided to use the XMR and MR chart because this chart is a good way to see the overall behavior of our process. We could use the X bar and the R chart, but with this X bar, that is another kind of chart within this variable group. Yes, thank you. It's kind of more specialized and sensitive because when you use the XMR, we are just we suppose that our data they came from just one subgroup, and when you use the XMR, we are dealing with an average for a subgroup with more than 1 point, so it's kind of more specific. But we just figured out that if we use the X bar instead of XMR, we are not going to see the overall behavior of our process, but the way that we are collecting the pH and the way that the pH meter is behavior. So it's kind of out of our original goal, and because of it we use the XMR chart. So here, as we can see, we have 1 point out of process specification, that is 6.09, and this is the lower point. Our kind of the higher value that we got was 8.63 over here, but it's not out of our upper specification limit, or our upper control limit. And this point out of control here results in 2 points out of control in our moving range chart. So we need to revise this, because when we are going to deal with these charts, we are just supposing that our process is going to have true variation for not assignable causes. So we need to revise this in order to have kind of good results to perform statistical analysis. So here, by revising the XMR and the MR chart, we just took out the 0.4 here that was out of control. And by taking this, our moving range chart kind of fixed itself. And we could see that because this point was pulling down the average, now when we took this out, the UCL and the central line here and the lower control limits, they were shifted up a little. And also our range here kind of changed, kind of a little, was kind of pulled out because of the 2 points that were kind of pulling this up. So now we can start to analyze our process. Here the moving range chart is useful because we can use this range to perform process capability and capability index analysis. So it's just why we use also this pair of graphs. Now here we just decide to plot all the data and to see how well was our points between the specification limits. And as Lindsay said, we have none of the points outside of the specification limits, just this lower point here that's kind of close to 5. But our average, as we can see here, is a little close to the upper specification limits. And we have some kind of things that we are going to discuss in a way to perform this better and pull this average down.
All right. Next slide, we can see here is a graph with specification limits and control limits together, so we can make a comparison between them. These lines that is between 5 and 9 are the specification limits, and these other two lines that are the narrow ones are the control limits. The specification limits is exactly for we see if our product is under the specification of the environmental agencies. And as Lucas said, our data doesn't show any problem with that. So if the environmental agencies come to Creamery, for now we are good. But if we look for the control limits, there is our control limit is a little bit above 9, which means that perhaps we can have points out of above 9 at page 9, and we were not able to detect it while we were measuring, but perhaps it can be there if the environment edges come and measure it. But mostly of that is under control. We don't have big problems right here. Here is a graph showing the overflow time that had an average of 40 seconds. This time varied because it's different lines that we were analyzing while they were cleaning tanks, or different kind of processing lines. So that's why the time here is different. And the biggest time that we had was 61 seconds. If we think for now it's not like that much time overflowing, but in a long term, I think we are going to have too much water wasted. So with too much water wasted, also a lot of money is going to put it on it to pay the fees. So if we can try to stop this overflow, can help the creamery to increase profits. And then here we have the process capability. The process capability here is greater than 1, which means that we are able to produce a waste that has a pH between 5 and 9. And the process capability index, that is the CK, shows if our process are going to be able to produce this waste under the specification. But as this value is lower than 1, is almost 1, but is lower than 1, it means that our process is not under control, so perhaps we can have points out of specification that maybe in the future can get the creamery in troubles. And in order for we have the CPK greater than 1, we can try to make the pH, the average of the pH of the waste goes down. So if the average of the pH goes down, we are going to have a process under control, and then our CPK would be bigger than 1. And also having this process, we are sure that we are not going to have points out of the specification, and at the same time we are saving water. And now about the conclusions of the project that Neil is going to talk.
So now let's talk about the requirements for the new tank. So like in every food processing facility, the equipments have to be made of some material that is easy to clean, corrosion-free, and smoothly bonded, so it won't accumulate food particles or dust or any other organic compound. So stainless steel would be the best one for this purpose, and plus stainless steel won't contaminate the food with any taste or color, anything. The other requirement is that it holds about 400 gallons of solution, so it would be enough to hold all the water for the largest CIP system that we have. And for if the company decides to make changes on the process with more equipment to clean, it will hold this water. Like sorry, the other equipment in the facility it has to be mounted off the floor, so it's easy to clean. Nobody has to lift anything or move anything, and it has to fit the available space that we have now, or the space that we will have if the company decides to expand the process, the space that they have. So we contacted 3 companies. 2 of them were indicated by the creamery, and both redirected us to this last one. How do I click to? Oh. This is Statico. Two companies redirect us to this one, and they gave us an estimate cost of $12,000 to $15,000. And also we contacted another one out of the state, I think it's Wisconsin, that is Enco Equipment, and this one estimated the costs about $10,000 plus the transportation and installation costs. Again, this is rough numbers. For exact numbers, we would need the number of connections and size of the connections and everything. We need to have more time and more information. So we're given like 2 options for the creamery. Leave the process as it is. So no, don't buy any other tank. Leave the overflow since the water is within the acceptable range. But this option here would be a little bad because the overflow is messy and it leaves the floor slippery, and the overflow is it is overflowing onto some pumps there, so we can damage some equipment. Or else the other option would be buy a new tank with the least expensive tank, price it at $10,000 plus the transportation and details, and the area will be safer for the creamery employees, and yeah, it would be a good investment for the creamery. So our suggestion is, even though the water overflowing from the recovery tank is within the acceptable range, we would recommend the creamery to buy a new tank, so the area will be safe for the employees or any visitor that is passing there. It won't damage any equipment because you won't have any overflow. With the new addition, we can prevent any future problems if the company decides to change the process, put more equipment there. So it will need to be cleaned, and more water is used. So the recovery tank, a new one, would be enough. And since the creamery would be expanding this the process, at least they are planning to, more equipment will be added, as I said, and as the area will already be in construction, they could add this new tank at the same time, so they won't need to stop the process and anything. And that's it. Questions?
I did have one question. In most of your suggestions, it's either do nothing or spend a lot of money buying a new tank. Did you guys look at any other option, like maybe finding a way to catch the water for like way less the cost than buying a new tank?
Well, either way, if you catch the water has to go into another tank, right? So that kind of, we group that in with buying a new tank.
Yeah, otherwise it would be like a messy, you just connect pipes to a new tank. So instead do all this messy, we just buy a new tank, and it's going to save more water. We can neutralize better the pH of the waste. So
Yes, you had a plot of your subgroup averages and said that they stayed within the EPA specification limits. What about just individual measurements? Did those stay within it?
Yes, they did.
They did.
Oh, if we look
Is that
back
an
at
earlier
the raw,
slide?
the raw data, none of the numbers were above 9. No. Yeah, so they're all, most of them are in the 8.
Actually, they didn't kind of vary a lot within each batch, so.
Yeah, they stay pretty much the same.
What happens in that batch for like numbers lower than the average?
I am not really sure why that happened. The process seemed to be the same to me, so when I was collecting the data, I'm not sure why it was different.
If the Greenway decides to buy a new tank, do you have any idea of what they are going to do with the old one? They are going to use?
They can sell it.
Could it be repurposed in some way?
Yeah, so it's
None of that
you
was
cream on
scope
your-
of their project, guys. Just gonna bring us back to Senate, and I know that.
I think you have a photo of what the system looks like. There's a rinse tank. and-
The one with the
Yeah,
water?
Right there.
That one?
So one end, the nearest end is a freshwater
Mm-hmm.
tank. And then about 2/3 of it going away from us there, that's the, what we refer to as the recovery tank. And so, as a little background, so when the plant was first built in 1992, the idea was this was going to be like a one-use type of system. So we wash a piece of equipment, and the recovery tank, we would just keep a little bit of water in there, but that would be our first rinse. When we wash the next piece of equipment. There's some residual soap in there. You see the pH is about 9
Mm-hmm.
in that residual there. So you get a pretty good cleaning just by rinsing out of that tank. So we weren't, at that time, thinking about trying to capture all of it. Over time, companies have come to put in larger recovery tanks because the more that we can recover, we can utilize that more than once
Mm-hmm.
to wash our equipment, or at least get the initial rinse. But then a year or two ago, when we found out that we were not in compliance with the city of Pullman requirements for discharge, then rather than emptying the tank after the caustic wash and starting over with and not even recapturing hardly any of the acid wash, we said, oh, well, if we put our acid and our caustic together, it'll neutralize it and we'll be in compliance. But then that's when we figured out, hey, we don't have a large enough recovery tank to hold both the caustic wash and the acid wash when we wash a piece of equipment. So probably if we were to replace that, we'd probably replace that whole thing with something that can handle a larger recovery tank. Another option might be purchasing a separate additional recovery tank that might be tied in together with the existing one. So we wouldn't have to pull this one out of the way, we just have to buy the larger recovery tank part, so that's what we're looking at.
Mm-hmm.
Is 400 gallons going to be enough with the expansion, with the membranes and everything they're going to be putting in?
We don't know how much water they would need to clean that, but as far as what they currently have, that would be way more than required.
It's likely that we're not going to use this CIP system to wash our membrane, because the membranes require a lot gentler type of cleansers.
Yeah.
And so they'll probably be cleaned in place with its own CIP system, or we'll just be manually adding stuff. So,
Okay.
yeah, the cleansers we use in this one would be too severe, or they could damage the
It would
membrane.
dry 'em out,
We
yeah.
try to use the same cleansers.
Gotcha.
I have a couple of questions. When you did your capability statistics, did you include that out of control point when you calculated those, or did you remove it before you did the calculation?
Was after removing the point.
Okay.
Yeah.
Okay, good. And then what eventually happens to that water in the recovery tank? So maybe you use it for a couple of rinses, then what happens to it?
It goes down to the drain that's right here, and that's, I think, what Alex's group was measuring.
Okay. Right, so then it is neutralized before, the stuff that stays in the tank, it does get neutralized before they put it in the
Yeah,
drain.
and that's why buy a new tank it's a good option, because overflowing it's pH 8. If you can neutralize, it's gonna be pH 6, so our process will be under control then. So that's why buy a new tank. Was for us the best option.
Okay. I find it interesting that you guys measured the pH is 8 or thereabouts when it overflowed, and they had significantly higher pH. Why do you think that is?
Because we measured continuously, and I think that we made a mistake in measuring before the water's actually neutralized. And so that really threw off our data. And that's kind of what I was going to say up there, but I didn't want to say it in front of while we were doing the presentation.
The thing is though, we measured it out of the drain every single time. So the
Well,
water
that's
is
not,
going down the
obviously
drain.
we didn't, obviously we were wrong. I'm just telling you, compared to their data, we did something wrong, did something wrong.
Or it
Or
could be.
they did something wrong.
It's different, you guys. They let them answer the question first, and I'll tell you what's going on.
It could just be that, so the water, they were collecting it, they started collecting at the very bottom of the tank, and we were collecting the top water, so maybe it didn't get mixed well enough.
Okay, I'll put my foot on that, I guess.
That
answer is
sounds
the same
reasonable
thing.
because one of your ideas was to mix the tank better, and so it could be that there's a pH gradient from the top to the bottom of the tank.
I think I mentioned something about homogenization of the neutralizer. Might be a reason for some of those data points.
So you guys could both be right, and this overflow is not as big a concern as the creamery was thinking, but what they're actually intending to put down the drain is a problem.
Are we good?
Other questions?
One question, I hope I'm gonna get, all 4 of the projects, I hope I get the data sent to me, is that possible?
Sure.
Yes, I can send you the PowerPoints, Russ, and then we're taping this right now, so I can also post all those videos to YouTube so you can see those as well, and so other people in the creamery can see it too. Hopefully I'll be able to pull that data this weekend.
Okay.